Hello everyone, my name is Vasilis Kontonis, and this is learning general half-spaces with general Massart noise under the Gaussian distribution. This joint work with Ilias Diakonikolas, Kane, Christos, Tzamos, and Nikos Zarifis. So learning linear classifiers is a fundamental problem in machine learning. We're given examples labeled according to some ground truth linear classifier f of x that has a weight vector w star and a threshold t star, and our goal is to recover this underlying ground truth half-space f. However, often the data have label noise. For example, a non-careful annotator may label some positive examples as negative and vice versa. In this work, we consider the well-known Massart noise model defined by Massart and Delek in 2006. In this model, the label of every data point x is flipped with probability at most eta. So for some fixed x, the noisy label y is equal to minus f of x with probability eta of x, that is smaller than this noise upper bound eta. Otherwise, the label x is equal to the ground truth f of x. The goal is to find the hypothesis h of x that achieves at most epsilon suboptimal classification error. The most general setting is the distribution-free setting, where no assumptions about the underlying x marginal are made. In this case, there are recent results showing that superpolynomial time is required in order to optimally learn half-spaces with Massart noise in the statistical query model. So those hard results motivate the study of the distribution-specific setting. In this work, we will make the fundamental assumption that the x marginal is a standard Gaussian. Starting with the work of Oasti, Balkan, Haktalab, and Erner in 2015, there is a long line of works that provide polynomial time algorithms for learning Massart half-spaces under the Gaussian distribution. More precisely, these works provide algorithms that have runtime and sample complexity polynomial in D over 1 minus 2 eta times epsilon. However, all these works crucially rely on two assumptions. First, that the noise rate is bounded away from 1/2. So observe that when eta gets closer to 1/2, the runtime and sample complexity go to infinity, because we have this 1 minus 2 eta factor in the denominator. Moreover, they assume that the underlying half-space is homogeneous. So this basically means that the optimal half-space f of x corresponds to the sign of w star inner product with x without the threshold t star. So the assumption that eta is bounded away from 1/2 may not always be realistic. It has been shown that non-expert human annotators often flip random coins for examples that are hard to classify. So when the noise upper bound is equal to 1/2, learning with Massart noise may initially sound trivial. How can we find the ground truth classifier if the training labels are purely random? The crucial thing here is that 1/2 is only an upper bound to the noise. So for example, we can have a set S that contains these hard examples whose labels are purely random, but since the annotators are usually correct, the probability of those purely random labels is small overall. So the probability of the set S is small. So even though the upper bound on the noise is 1/2 in this case, there is still non-trivial signal in the training data, and in particular, in this case, the optimal classifier has error equal to the probability of the high noise set S over 2. Since outside of S there is zero noise. So in this setting, it is reasonable to ask for a half-space H with epsilon suboptimal error. We basically allow it to be incorrect inside S, where the labels are purely random, but should be correct for the rest of the space. The second assumption that we discussed is that the underlying optimal half-space is homogeneous. So to begin with, it may seem that adding a threshold doesn't make a big difference. And this intuition comes mostly from the fact that in order to reduce the general case to the homogeneous, we can simply add a constant feature to all data points x, so we map x to x, 1, let's say, and then give those examples to an algorithm that learns homogeneous half-spaces. However, this trick only works when the homogeneous learning algorithm works in the distribution-free setting. When we perform this transformation, the resulting distribution is no longer Gaussian, and therefore we cannot use the homogeneous learning algorithm of the prior work because all these algorithms have distributional assumptions. The main question that we investigate in this work is whether we can remove any of those two assumptions and still obtain efficient algorithms. Before we go into the results, we first define the well-known statistical query framework of Cairns, where instead of having access to individual examples, the algorithm can access expectations of boundary functions over the data. More precisely, the algorithm can pick a query function q that depends on the data point x and the label y, and get some number q hat that is approximately equal, so we have some tolerance tau here, to the expectation of the query function q over the labeled examples. So the class of statistical query algorithms is very broad, and in particular, all learning algorithms for noisy half spaces that we have discussed in the prior work fit in the statistical query framework. So we can split the space of learning noisy linear classifiers in different regimes, going from the most limited to the most general. So the most limited case is when the optimal half space is homogeneous and the noise upper bound eta is bounded away from one half. As we already discussed, in this case prior work gives polynomial time algorithms. On the other extreme, the most general case corresponds to considering general half spaces and not even assuming that eta of x is smaller than one half. So it turns out that this noise model is equivalent to the well-known agnostic model, in which case it is well known that with d to 1 over epsilon squared samples and runtime, we can learn general half spaces. Moreover, in a recent work, it is shown that in the statistical query model, this is also best possible. In this work, we focus on the regions between these two well-explored extreme settings. We first investigate the case where the noise is bounded away from one half, but the half space is general instead of homogeneous. Our first result is an algorithm with d to log 1 over epsilon sample complexity in runtime that finds a half space with epsilon suboptimal classification error. We see that we have a substantial increase in the sample complexity in runtime from the homogeneous constant bounded noise regime, and it's a natural question whether this quasi-polynomial dependency on epsilon is actually necessary. Perhaps surprisingly, our first lower bound shows that this is essentially best possible. So assume that there are no high noise points, so for every x, the Massart noise is at most 1/3, and that the underlying half space is general. So it has a threshold T star. Then any statistical query algorithm that learns general half spaces either requires statistical queries of tolerance d to minus log 1 over epsilon or has to make exponentially many queries. To better understand what this statistical query bound means, notice that in order to implement a query with such small tolerance, then basically d to log 1 over epsilon samples from the underlying distribution are required. We next consider the case of homogeneous half spaces with general Massart noise. So now the upper bound of the noise is 1/2, and we have these high noise points that we discussed earlier. In this case, we again show a quasi-polynomial lower bound in the statistical query model. So any statistical query algorithms that find a hypothesis h of x with epsilon suboptimal error either requires quasi-polynomial accuracy or exponentially many queries. So far we have shown that removing either of the homogeneity or bounded noise assumptions results in a substantially more challenging learning problem that requires quasi-polynomial samples at runtime. Moreover, for constant bounded noise, so when eta is bounded away from 1/2, we have provided a matching upper bound. So we have given an algorithm that learns general half spaces with d to log 1 over epsilon samples in runtime. Given these lower bounds, our final and most general question is whether we can provide a quasi-polynomial algorithm that learns general half spaces under general Massart noise. So can we remove both assumptions at the same time? We give an efficient algorithm that draws d to log 1 over epsilon samples and finds an epsilon suboptimal half space. The sample complexity and runtime of our approach are qualitatively optimal modulo an exponential overhead in the accuracy parameter epsilon. So our runtime is d to log 1 over epsilon times 2 to poly 1 over epsilon. Taken together, our results provide a fine-grained picture of the complexity of learning half spaces under Massart noise. Moreover, our results establish the following interesting threshold phenomena. For homogeneous half spaces, going from constant noise to 1/2 increases the complexity from polynomial to quasi-polynomial, and then going from eta equals to 1/2 to greater than 1/2, which corresponds to the agnostic setting, increase the complexity from quasi-polynomial to exponential in epsilon. Moreover, going from homogeneous to general half spaces, which basically corresponds to adding just one single parameter to the model, also results in quasi-polynomial runtime and sample complexity. So both these threshold phenomena are perhaps surprising. I will now go briefly over our techniques focusing on algorithmic upper bounds. We start with the algorithm that learns general half spaces with constant bounded noise with d to log 1 over epsilon samples and runtime. So at a high level, our algorithm is based on the certificate framework developed by Diakonikolas, Kane, myself, Tzamos, and Zarifis in two prior works dealing with learning half spaces under Chubakov noise. The certificate framework relies on the following characterization of the linear function L star corresponding to the optimal half space. So for L star, it holds that for every positive function t of x, we have that the expectation of L star times the label y times t of x is greater than or equal to 0. On the other hand, for every other function L that is different from the optimal L star, there exists some non-negative weight function t of x that makes the same expectation strictly negative. So there is some reweighting of the space so that this expectation of L times the noisy label y is negative. So this characterization basically tells us that we have to solve an infinite dimensional linear program that asks for some linear function L whose expectation is non-negative for all non-negative weight functions t of x. So this linear program has infinite constraints. In order to be able to solve this linear program efficiently, we have to implement a separation oracle. So this means that given some suboptimal L, we have to efficiently compute a weight function t of x that makes the corresponding expectation negative. In other words, we have to find a violated constraint for the suboptimal guess L of x. Our main technical contribution is an efficient separation oracle based on SDP that requires d to log 1 over epsilon samples and runtime. Okay, so assume that the optimal function f of x is very biased and is positive on the small blue region shown here that is far away from the origin and has a very small mass, say 10 times epsilon, where epsilon is the target accuracy here. So the constant hypothesis that guess is -1 for every x has error at most 10 times epsilon, which is small, but we still need to improve it. So we have to find the certifying function t of x for this constant guess. Basically, we want to find a function t of x that makes this expectation negative. So if we expand this expectation with respect to the label y, we get two terms. The red term that corresponds to the agreement region, so when the sample is left of the half space, the constant guess agrees with the optimal half space. And the blue term that corresponds to the disagreement region. So for x1 greater than the threshold t star, f of x is positive, but the constant guess is negative. So the worst case noise will try to convince us that the constant guess is good and set eta of x equals 0 in the red region. On the other hand, in order to hide the disagreement as much as possible, we'll maximize the noise in the blue region and set eta of x equals to the upper bound eta there. However, in this setting, the upper bound eta is some fixed constant, say 0.499. So the contribution of the blue region, that is negative, is only downscaled by a constant factor. So reweighting t of x should try to put as much weight as possible in the blue area in order for the blue term to win and make the total, the sum of the two terms negative. An obvious choice is to pick t of x to be the indicator function of the disagreement region. However, recall that we don't know the direction of the optimal half space f of x, so we have to optimize over it. So if we parameterize t of x with the vector v and try to minimize this expectation with respect to v, we get an optimization problem that is non-convex. So it's unclear whether solving this problem is easier than the initial problem of actually learning W star. As a first step, we have to at least try to make the certifying function t of x smooth. So initially, the Gaussian is centered at 0. And if we could shift the Gaussian to lie well inside the blue region, we would put a lot more weight to the blue points and would make this expectation negative. In order to do this, we can simply set t of x to be the exponential function e to c times x1. So x1 is this coordinate of the horizontal axis here. So when we have a large enough constant c, we essentially move the mean of the Gaussian to the right of t star. So we move the Gaussian well inside the blue region. And this certificate is now smooth, but again we have to optimize over the unknown direction. And this again results in a non-convex objective, so it is hard to optimize over V. The main idea is to replace the exponential shift by a positive polynomial. So we can always expand the exponential function as a polynomial of infinite degree by taking its Taylor expansion. And because the Taylor expansion of the exponential function converges very fast, we can show that basically truncating to degree roughly log 1 over epsilon is good enough. So because we want our reweighting function to be positive, we're going to take the square of the Taylor expansion polynomial. So now the optimization problem is to find a low degree polynomial so that this expectation is negative. If we parameterize the polynomial by a vector v, inner product with the moment profile vector m of x, so m of x contains all the monomials, x, x squared, x cubed, etc., then since the polynomial is a square, this basically corresponds to finding a negative eigenvalue of a symmetric matrix. So this is a problem that can be solved efficiently. So this is the main idea of our algorithm that works for learning general half spaces under constant Massart noise. We will now go over the main ideas of the algorithm that removes both assumptions and learns general half spaces with general Massart noise. Our basic algorithm in this case is an iteration which at every step tries to decrease the angle between the current guess w and the optimal direction w star. So we consider an iterative update rule that at every step adds some update vector v to the current guess and then renormalizes so that we stay on the unit sphere. Assume that initially our guess and w star are orthogonal. So we then have to find an update vector v that correlates positively with the optimal direction w star. So basically we want v to have positive inner product with w star. And in this case, updating with such a vector v will improve the angle between our guess and w star. So w prime, after the update, will move closer to w star, to the optimal direction. In fact, we will be more lax and simply ask for the update vector v to correlate with non-trivial probability, say 1/3, with w star. So basically we want to find a v such that with probability at least 1/3, v inner product with w star is greater than some correlation lower bound gamma. So now, if the correlation is lower bounded by gamma, the angle will decrease by a factor of 1 minus poly gamma. Therefore, in order to reach angle epsilon with the target w star, we roughly need poly log 1 over epsilon over gamma steps. So since every iteration is successful with probability 1/3, the probability that all steps, all update vectors point in the right direction is going to be roughly 1/3 to poly log 1 over epsilon over gamma. So in order to achieve constant probability, we have to restart this iteration roughly 2 to poly 1 over gamma times. So an easy way to find vectors that correlate with the optimal direction is to simply pick uniformly random vectors from the unit sphere. Then, with probability at least 1/3, v will have roughly 1 over root dimension correlation with w star. However, as we said, this would result in a number of restarts exponential in the dimension, which is too large. So in the noiseless case, we can do much better than randomly guessing the update vector v. In fact, the degree 1 tau vector, so this corresponds to the expectation of x times y, will be exactly parallel to the optimal direction w star. However, this is no longer true in the noisy setting that we are considering here. In order to cope with the noise, our main idea is to use higher moments in order to find a good update direction v. So basically we want to look at the expectation of y times x tensor k, which is a higher order tensor. Our algorithm computes the order k tau tensor, which we can then view as a d by d to k minus 1 matrix and compute the subspace spanned by its top left eigenvectors. So this basically corresponds to finding eigenvectors whose eigenvalues are larger than some threshold. We then saw that if we pick a random direction in the unit sphere of this subspace, so instead of picking a uniformly random vector in the unit sphere of Rd, we're picking a uniformly random vector in V, we can then achieve correlation poly epsilon instead of 1 over root d. This means that using such updates, the number of restarts is no longer exponential in the dimension, but only in 1 over epsilon. So in order to achieve good correlation with a random vector chosen from V, we have to show that the optimal direction W star has non-trivial projection inside the subspace V. And to do this, we basically have to construct a mean-zero univariate polynomial P that when we evaluate P in the direction of W star, we obtain good correlation with a noisy label Y. So the mean-zero condition here is important because if we increase the correlation by adding large constants to the expectation of P, this basically doesn't reveal any useful information about the optimal direction W star. So we really need the polynomial P to be mean zero. Our main structural result shows that there exists a univariate mean zero polynomial of degree log 1 over epsilon that achieves correlation poly epsilon with a noisy label Y. So let's now see why this is true. Assume again that the optimal threshold is the optimal half space is positive right of the threshold T star and negative on the left. One way to achieve good correlation with Y is to find a polynomial that approximates the sign function pointwise, and this idea has been used in order to learn half space with adversarial noise. However, the required degree in this case is poly 1 over epsilon. So such large degree is actually necessary when we deal with adversarial noise, because the adversary may carefully pick some regions, shown in purple here, and completely flip the sign in these regions. However, this is no longer possible under Massart noise. So in this case, the flip probability eta of x is everywhere bounded by 1/2. So for any x, the expected sign is still correct. Basically, the adversary can zero out the contribution of some subsets of the space, or simply rescale it to some smaller value, but they cannot flip the expected contribution for any x. Therefore, instead of approximating the sign function pointwise, we only need to find a polynomial that matches its sign. Our main structural result shows that there exists a univariate mean zero polynomial of degree log 1 over epsilon, whose sign agrees everywhere with the optimal half space. Therefore, since the Massart adversary can only downscale the contribution of regions and cannot flip their expected sign, one can show that such a sign matching polynomial also achieves poly epsilon correlation with the label Y. So let's now recap the main steps of our algorithm and conclude with its total runtime. So in order to compute the update vector V that we use in our iteration, we have to compute the order k Chow tensor, and this takes roughly d to log 1 over epsilon runtime. Then, in order to reach angle epsilon with W star, we basically need poly 1 over epsilon iterations. So we need poly 1 over epsilon such updates, and as we already discussed, we basically need to restart this whole approach roughly 2 to poly 1 over epsilon times. So the total runtime is d to log 1 over epsilon times 2 to poly 1 over epsilon. So I would like now to conclude with a summary of our results. So we first prove a statistical query lower bounds, showing that both learning general half spaces with constant bounded Massart noise or learning with general Massart noise, so when the upper bound eta on the noise is 1/2, are both problems that require d to log 1 over epsilon runtime ensembles in the statistical query model. So these are both challenging problems. Now our first upper bound is an algorithm that can learn general half spaces in the constant bounded setting. So assuming that eta is bounded by, say, 0.499, we give an algorithm that can learn general half spaces with d to log 1 over epsilon runtime ensemble complexity. Finally, in the most general setting of general Massart noise and general half spaces, we give an algorithm that has runtime d to log 1 over epsilon times 2 to poly 1 over epsilon. So some interesting questions for future work is, first of all, whether we can remove the exponential overhead for the general Massart noise setting. Our lower bounds do not have this term, so it's interesting to investigate whether we can get algorithms with just d to log 1 over epsilon runtime. Another interesting question is whether we can get results for other concept classes, for example polynomial threshold functions, even in a constant bounded Massart noise setting. And finally, Since just adding a threshold to the class of half-spaces increases the complexity from polynomial to quasi-polynomial, it is perhaps interesting to investigate whether there exist milder noise models that are closer to the random classification noise model that allow for provably efficient algorithms. Thank you.